Hola. Hello, hello, hello. Audio check. 1, 2, 3. Yellow. Let me see. Audio check. A bit low. Do we need to turn up the gain? Let's see. Oh, I'm just gonna talk about what we're gonna do today. So today, I think I'm going to we are disconnecting and reconnecting. Great. Just great internet, isn't it? Let's see. Stop that for a second. Let's see. Oof. Internet. Jesus, the bitrate is terrible. Alright. That's enough of that. Welcome. Alright, let's try to get that cutter machine working. I'm gonna try to solve the maze walker. Maze solver. What was the command to test? Was it just maze? I think it was. Okay, cool. Okay, so yarn just makes. If I remember back when I was solving these every day, pretty sure we have to pass in the maze itself, we pass in the wall stream, we pass in the current, and the endpoint. And I think we also, oh right, we have the Boolean. Is bool a thing? No, it's Boolean. Okay. I think we have to pass in the path, which we're gonna return by the end of this private recursive function. We have the base. Let's see. I wonder if that's good enough for the people watching. Yeah. Oh, Jesus, this is big font. Export defaults no function. I remember. Oh man, how do you even declare a variable again in TypeScript? So let scene. You do this? I remember. Is that a thing? Let path be point. And you'll just return path. I think, if I'm not mistaken, this returns a boolean later on. We'll see why. Path. Frames again. Oh god, I can't even remember how to do this. Maze? Length. And J. Maze. What are we doing here? In my J. Pos. I think that's, yeah, we're just initializing it. Actually, do we array? How do we create array again? Yeah, right. Maze length. Fill, I think. Oh, jeez, I can't remember how to do this. Fill. These all random so start negative. Turns modified array. Ooh, today's internet is really not helping. Let me check something for a second. I'm lucky I'm just kind of coding streaming. Oh, sorry, streaming coding. Otherwise, the dropped frame is probably gonna be really fucking annoying. Point is just X and Y, so yeah, we'll just leave it there for now. Can't remember how you do it. Okay, I think, yeah, I remember. I think you just kind of do a for each. It's just basically the same thing what I was doing, but... Oops. You just all array elements from start to an index static value. I think it was this. Oh, right. That's why we need the for each. Don't need the value, we just need the index, I think. Pretty much, I think. Oh, right. Yup. Okay. cool. And remember. We do the boundary case, less than 0. Or equal to I think the x is the right, it's reversed. Length. Wait a minute. I guess it doesn't really matter. We can just pick one. Current dot y less than 0 or dot y is greater than the base dot length. Why is there an error? Alright. What else? Oh, you gotta kidding me. Wait, why is it not properly indenting me? There no, we would not have like a prettier for TypeScript or something. Let's see, what else? So if we're hitting a wall, I guess, equals, well, maze current dot x equals wall and false. Is out of bounds, bumping into walls, and then if I guess if we reach the end, if x and current y equals and we've reached the end if this is the case, and then if I'm pretty sure there was another one, I can't remember. Oh right, if we've been here before. Deja vu. We've seen it. If we've seen it. X. We've seen it. Turn false. Perfect. Now to the recursive case. So we first flip the bit. This. Current X. True. Now we do something like this. This is the 4 cardinal directions. And we'll start from left. Left. Up. down. So we're gonna loop over that. Length. Current direction. We're just going to walk again in the current direction. Given the maze, given the wall, given the new point. Oh. Sense corridor. Point is the current x plus corridor 0, and then the other one is just current point plus corridor 1. Oh, right. Yeah, I forgot about that. I thought this was Lua. Hee. And now we walk it. Maze, wall, new current. Give it the end, give it the scene, give it the path. True. So if we walk and we find the end in the recursive case, return true. We need to append the path. Where are we appending the path? Let me see. To pop it, right? The last element of the array, right? We push it here, and we loop through it. We don't find anything at all. We're going to pop it, and then return false. I think that's it, maybe? Alright, let's try it out. Cannot read properties of undefined reading 10. What? Cannot read person of undefined read. What do you mean? Oh. Cannot read properties of undefined. Wait, what's the current then? Boop. Did printing it at home? Man, how do I... Okay, there we go. X is 10. Reading 10. Oh, that's why. Oh. I wonder what this looks like. Honestly, I probably initialized this incorrectly. Scene. Ooh, 6 empty items. Yeah. You know what? I'm just gonna do it explicitly. F this shit. 4. Oh yeah, I just remembered. Oh, I see. Yeah, okay, I remember now. Never mind. Never mind. Never mind. False alarm. Bill. False. I think this is how you do it, right? So we loop through the first dimension of the array, of the maze, sorry, and then we make sure that each row is filled with string length of that row with false. Yep. Alright, cool. Dun, 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 dun. Nice. Oh, we're so close. We're so fucking close. We're so fucking close. We're so close. What is this? Guess we're just missing that last bit. Wait, so... Let me see. Right, so we're already in the right track. We're just missing that last bit. What is that last bit? So this is the result, which is, I'm guessing this is the start, and this is the end or something. Oh yeah. You hear maze solver. Maze wall start. Yep. So start is 10:0. finish at 1.5. So, and oh right, 10. Okay, so this is the start. Oh. Zero, 1, 2, 3, 4, 5. So 0, 1. This is the end. This is the start. Oh, we're literally just not appending the end. Okay. Oh, that's why. Yeah, I remember this. I also saw this back when I was solving this for the first time. Completely forgot about that. Basically, we just need to append the last point as we finish the maze. We've looped through here. We've actually seen the thing. We've seen the end or the exit. But because we're not going through here, we're going here directly. And we're turning true. So we're not pushing the current. Which means we should fix it. Oh yeah, buddy. Okay. So what was wrong with this one? I'm pretty sure I basically did the same thing here. Boundary. Out of bounds. We're just not doing the wall because we want to step through the wall. So this is the scene. Current y current x equals true. This is us stepping to the wall and then changing the type. If it's a wall, change it to a tile. It's not, or the beam, or the goal, the yellow thing is inside a wall. Maybe we need to see, but I already did it. So why is it not changing? I don't think we need to do this. Interesting. Oh. Hmm. What the heck? I really wish I could debug this somehow. I have no clue how to debug it though. Actually, I might just put it. So, this is a boundary condition, right? But we're just not gonna return false. We're just gonna literally do what we're doing here. Actually, we might just put it up here so that we don't need to do it again down here. Let's see. Just make it clear up here. Tight wall, then we're going to change that thing to da 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 da. This is kind of ugly. I don't like this formatting. Let's see. Can we change it somehow? Wait, what are you? Gamma 4, E4B. Okay. I want to change you. What are you? Gamma 12. What? Quit it for now. Be this. Oops. Damn it. Alright, hopefully that works. Anyways, where were we? Maybe I need to do this. What's the equivalent of a path pop in here? Do I return the original thing as a wall? Not sure. Well, what the heck? Why am I not getting a response? Is Olama off or something? Okay, that's why. Darn it. Whoa, what the? Maze Queen, Shinking. Content. Oh, hello. Yes, it is a pointer to pointer bool. I was trying to do a 2D array, but then I realized C doesn't do well with 2D arrays. Boy, this is taking a while. Clang format. What the? Break before binary operators. Hello again. Oh, How are you doing? Client format. Truck initializers. Format. Back arguments. Also, this look like it's true. Bin pack arguments. Pretty good, just checking in. Seeing you tidy up stuff though. Nice. Yeah. Thanks. I wouldn't say it's tidied up, but yeah. Trying to. Hope you're having a good day. Impact parameters. maze. That's not changing anything. Ugh. Oh well. Oof. Where was the sacrifice? Oh right. Gotta check this first. Oh. Oh. Oh, but it clears everything. Oh. Oh. Yeah, I guess it works, but it just clears everything. Oh boy. I'll turn it into a wall. Oh. Okay, I mean, it kind of works, but yeah. Yeah, I mean, it works. It does what it says on the tin. It clears a path for the maze. But it's not much of a maze because it clears everything. Yeah. All right. Oh, I just realized. We got 10 followers. Nice. Super happy about that. Need maze generate. Oh, let's see. I want to have browser. Maybe this one. Maze gen. Web browser. Heck. How do people generate maze? Let's watch this one.
As kids, we've all played Pac-Man, navigating those mazes, eating dots, and dodging ghosts. These intricate pathways made the game exciting and challenging. But have you ever wondered how such mazes are created?
Yes.
First, let's ask the question, what's a maze?
What is a maze?
A maze is a complex network of paths or passages, where the challenge is to find the correct route from the starting point to the finish.
Right.
Mazes can have multiple dead ends, and only one or a few ways to solve them, making them both puzzling
Let's speed this
and
up,
fun.
please.
Creating a maze isn't just about drawing lines and placing dots. It involves thoughtful design and clever algorithms. Designers carefully plan the maze layout to ensure it's challenging but not frustrating, while algorithms generate complex pathways and dead ends to keep players engaged and entertained. But what about a perfect maze? A perfect maze is a maze where every point is reachable, and where there is only one single path from one point in the maze to any other point. In this video, we're going to explain how perfect mazes are created, explore some algorithms that enable us to draw mazes, and walk through the origin shift algorithm, which enables us to create mazes that keep changing while still being perfect mazes. Let's start with the depth first search, or DFS maze, also known as the backtracking maze.
Tracking maze. Yep.
To generate a maze using the depth first search, or DFS algorithm, we start with a grid where every cell is surrounded by walls. We select a random starting cell, mark it as visited, and then look at its neighboring cells.
Yep.
From these neighbors, we randomly choose one that hasn't been visited yet, move to this
that's
cell,
what I did.
mark it as visited, and remove the wall between the current and chosen cell to create a passage. If we encounter a cell with all neighbors visited, we backtrack to the previous cell and continue the process. This exploration and backtracking create a complex network of passages. The maze is complete when every cell is visited and connected, forming a single continuous path between any 2 points without loops. Now we move to the hunt and kill algorithm.
Hunt and kill.
The hunt and kill algorithm starts with a grid full of walls and a randomly chosen starting cell marked as visited.
Right.
From this starting cell, the algorithm explores its unvisited neighboring cells. If any unvisited neighbors are found, the algorithm moves to one of these cells, removes the wall between the current cell and the new cell, and marks the new cell as visited. This process of moving and removing walls continues as long as there are unvisited neighbors.
You see, I guess the thing that's different with them is they're differentiating between a position that you can occupy and the wall itself. Whereas I'm kind of, not by design, but kind of made the position you can occupy a wall as well. So it's either a tile or a wall. And that's probably the difference here, which is, I wonder, would have worked probably if I just had like a thin wall instead of like each grid can be a wall or a tile. Oh well. Moving
When
on.
a cell becomes a dead end, meaning it has no unvisited neighbors, the algorithm hunts for any previously visited cell that still has unvisited neighbors. It then moves to the cell and continues the maze generation process. The algorithm repeats this hunt and kill cycle until all cells in the grid have been visited and interconnected, resulting in a complete maze. Now to the
Wait a minute, let me think. Right now, it's looping through. Let me see. Oh, right, I have the tab browser on. Right now, I have this, which is looping through the direction in a kind of left, up, right, down order. What if we loop through it in a different order every time? That make a maze? Hmm. Maybe later. That's a good idea to try though.
Prim's maze algorithm. Prim's algorithm for maze generation is a process that starts with a grid full of walls and selects an initial cell as the starting point. It marks this cell as part of the maze. The algorithm then maintains a list of walls adjacent to cells already in the maze. At each step, it randomly selects one wall from this list, and if that wall separates a cell inside the maze from one outside, it removes the wall, adds the new cell to the maze, and updates the list of walls to include those adjacent to the newly added cell. This process is repeated until all cells have been included in the maze. The result is a maze with interconnected pathways, ensuring a single connected component with no isolated sections. Now, let's move on to the origin shift algorithm. This algorithm, invented by a Minecraft player, helps us generate mazes that continuously change while ensuring they remain perfect. The origin shift algorithm starts with a perfect maze. Here, arrows represent open paths and lines represent walls. For example, imagine a maze where all cells are oriented to the right, except for the cells in the rightmost column, which are oriented downwards. In this example, our origin is the cell at the bottom right, which has no direction. We start with an origin cell and randomly select one of its neighboring cells. This new cell becomes the new origin. Then, we do the following steps. 1. Add an orientation or direction from the previous origin to the new origin. 2. Remove the wall between the cell and randomly select one of its neighboring cells. This new cell becomes the new origin. Then, we do the following steps. 1. Add an orientation or direction from the previous origin to the new origin. 2. Remove the wall between the previous origin and the new origin if it exists. Next, we update the new origin by 3. Deleting its previous orientation. 4. Adding a wall in the direction where there is no orientation. By repeating this process, we continuously shift the origin, creating a dynamic and ever-changing maze.
A what?
Shift the origin, creating a dynamic and ever-changing. 3. Deleting its previous orientation. 4. Adding a wall in the direction where there is no orientation. 3. Deleting its previous orientation. 4. Adding a wall in the direction where there is no orientation.
Wait.
Or direction. from the previous origin to the new origin.
Mm-hmm.
2. Remove the wall between the previous origin and the new origin if it exists. Next, we update the new origin by 3. Deleting its previous orientation. 4. Adding a wall in the direction where there is no orientation. By repeating this process, we continuously shift the origin, creating a dynamic and ever-changing maze. Now let's take a look at the implementation of different algorithms. The source code is provided in the description below. Feel free to play with the parameters to see how they affect the algorithm's behavior and performance.
Hello everyone. Today I wanted to share with you a new maze generating algorithm I came up with. I looked everywhere online and I couldn't find anything like this. But if any of you know of an algorithm that is similar, then please let me know in the comments. A while back, I was looking for an algorithm to use for my upcoming Redstone Maze Generator version 2. I wanted to make this new version a lot smaller than the first, and I just didn't see how I could do that if I stuck with the same algorithm. So I did a bunch of research to find an algorithm with much simpler logic, but I couldn't find anything that was quite what I was looking for. The closest thing I could find was the Aldos-Broder algorithm, but while the logic for this algorithm was incredibly simple, it also had a random runtime, which wasn't ideal. So I tried coming up with my own algorithm, one that would be specifically suited for implementing using Redstone. My goal for this algorithm was for it to have as simple logic as possible, while also having a decent enough runtime. I also wanted this algorithm to result in a perfect maze, that being a maze with no loops or isolated areas. And after a lot of head scratching, this is the algorithm I came up with. We start with a grid of nodes. Each node has a direction property that can either point up, down, left, right, or nowhere. Next, we initialize the grid to be any perfect maze. Now, this may sound a bit silly since the entire purpose of the algorithm is to create a perfect maze, but hear me out. We can use this as our starting point. Every node points to the rightmost nodes point down, and the bottom right node points nowhere. We will call this node the origin node. This is a perfect maze. It doesn't look very fun to solve, but technically it meets all the requirements of a perfect maze, so it will work to a random neighboring node. That neighboring node becomes the new origin node.
Right.
Finally, we remove the origin node's pointer. That's it. That's the entire algorithm. Now let's finally along. Next, we repeat to a random neighboring node. That neighboring node becomes the new origin node. Finally, we remove the origin node's pointer. That's it. That's the entire algorithm. Now let's see it in action.
This is insane.
So when do we stop? Well, that's the cool thing about this algorithm. You can stop at any time you want, and the resulting maze will always be a perfect maze. If
That's
you want
crazy.
a maze that is similar to the original with some differences, you can run it only for a bit, or if you want an entirely new maze, you can run it for longer. But generally, I find that if you're running
you're lurking? Okay.
for the maze width times the maze height...
Yeah, I'm just learning about maze gen right now. Really cool. Very cool.
times 10 iterations, it will result in a pretty unique maze, with occasionally a few remnants of the previous maze.
Damn. That's pretty sick.
So how is it that performing these 3 steps on any perfect maze will always result in another perfect maze? To understand this, let's first define a set of rules that a maze must follow in order to be considered a perfect maze. 1. Every node except for the origin node must point to one neighboring node. 2. Every node must be connected to the origin node. Let's delve into the first of the 2 conditions. Here is a simple example. What is the minimum number of connections required to connect 3 nodes? The answer is 2. How about 4 nodes? The answer is 3. It doesn't matter where the nodes are located or how we connect them, we will always need one less connection than the number of nodes.
Right.
Let's scale this up to our maze. Here there are 25 nodes and 24 connections. This explains why we can describe mazes by having each node point to exactly one other node with a single node pointing nowhere. We're essentially pairing up each connection with a node and leaving a single node behind. But this rule by itself doesn't assure that the maze will be perfect. Take a look at this maze, for example.
Yeah.
This maze satisfies the condition, but it contains one loop and one isolated area. This is why we introduced the second condition. Every node must be connected to the origin node. In other words, if you start from any node and travel along the arrows, you should eventually reach the origin. This assures that there will be no isolated areas, and because a loop requires nodes to point to each other in a cycle, this rule also ensures that there will be no loops. This is why the algorithm works. When we move the origin node, we remove its pointer, and we have what was previously the origin point to the new origin. After the iteration, the origin node is still the only node that doesn't point anywhere, satisfying the first condition. And by always pointing to the new origin, we assure that the origin node will always be connected to the rest of the maze, satisfying the second condition. So when should you use this algorithm? Well, outside of the one case I specifically designed it for, that being Minecraft, this algorithm isn't the most practical out there, but there is one interesting use for it that I don't think any other algorithm has. Since after every iteration the maze will be perfect, you can actually play the maze while it's generating. So if any of you game designers out there want to implement a maze that shifts and changes around you into your game, then you can give this algorithm a try. So that's all I have for you today. In the description, I've left a link to the JavaScript I wrote for the algorithm, so if you want to see how the algorithm looks in code, you can check that out. And feel free to use this algorithm in your builds and stuff. If you would like to learn more about maze generation, check out this web app by fellow YouTuber dQWERTYC. It allows you to test out a bunch of different algorithms, as well as letting you go through the algorithm step by step. It's a very helpful app that I highly recommend checking out. I'll link the app and his channel in the description. Make sure to subscribe so you don't miss the next video where I implement this algorithm in.
Wow. Maze gen. See, that's pretty cool.
Hello everyone. Today I wanted to share
Which generates a perfect maze over every iteration. Algorithm has been discovered. Proof of Markov in tree theorem. The origin shift.
Back in January, Captain Luma uploaded a video detailing a new maze-generating algorithm they had come up with, which they would eventually name Origin Shift. It can gradually change a maze over time, with the benefit that you can stop it at any moment and get a perfect maze. The video started to see a lot of interest in June, with Matt Batwings also featuring
with you a new maze-generating algorithm too. I wanted to make sure this algorithm was incredibly simple. It also had a random runtime, that being a maze with no loops or isolated areas.
How do I make it my own though? Kind of stuck. Maze generation.
Let's make a maze generator in C++.
Let's generate a maze.
Okay, so now I'm gonna set a dimension so it's.
What the? Oh, right. Hmm. Hmm. Large chunks of the area. Hmm. I guess that's what we need a path for. Need to go to the restroom. Be right back. Let's pause this for a sec. Bathroom break. want to see the path. Same thing here. Just say it's a... Oh, we don't know how big it'll be. We'll just allocate it. Path. Nope. This should. Path. Oh, I don't know how big it should be. Okay, let's just say, I don't know. World. Right. Ooh. I'm gonna sneeze. Oh god. Whew. Yeah, I guess it makes sense. Path. Let's see. Oh, I don't know if I can. Can we do printf of that thing? I don't know if we can even see into that. Okay. So I just wanna see what the path is that it takes from start to end. Or okay, let's see. So we're at 113 basically, yep. It starts to move 112, which is left. Keeps going left, 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 and then it moves up. And then does it move up? No, actually. It moves down. Yeah, wait a minute. Oh wait, no. So it went up and then probably found a boundary. Wait, no. Oh, this is all the way to the left. And it went down. What the? That's weird. I'm expecting it to move up, not down. Right, so it goes 2, 0, 2, 1. Second, a third roll. It's moving right. And then once it gets to the rightmost thing, moves down and snakes a path. I see. All the way until it gets to 3, 3, which is fourth row, fourth column. 1, 2, 3, 4. Yeah. 1, 2, 3. So it is doing its job. 2, 6, moves left, moves up again, goes right, all the way to the end. Yeah. Think Pokemon Mystery Dungeon. I see. Infinitely changes for how does a path get through? What rules dictate wall over walls? Maze here. There's backtracking. Don't find a path. They build and find a network. Be sure if a was eventually connected, but never accidentally. It's a straight shot through. Given your current setup, a grid where any cell can be a wall or a tower. You currently reading initial state based on geometry rules or letting pathfinding. I'm letting preserving. I'm currently letting the pathfinding dictate where the wall should be. Oh boy, okay. So it's not about pathfinding. I see. Oh well. I see. I see. Fundamentally flawed. Maze generation. Not 22. What do you say again? Let's see. I'm just gonna play Everything is Crab to wind down. Do, 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 do. Do, do, Yay. Change this into this. There we go. Challenger, personalizations trigger 1 level early, please. Passive. Pioneer. Every 12th level up is a branching evolution. Leech. Ooh. Good stuff early on. Alright. Look at him. Little cute mouth. Eating speed, physical. Let's get some feeding speed early on. Oh. Frame rate is terrible. Ooh, okay. Probably gonna need to stream at 60 next time I play games. Beat. Alright, we're going the ability route, I guess. Beak. Do we want plating? I want plating. Ooh, +5. Nice. Ouch. Spine, nomadic. I like spine. Correct. Ooh, is this a hallucinogen? Nope. Vortex ability. Yes, please. What? What? Saliva. Ooh, immune system. Ooh, beak. Saliva again. Yeah, I'll take it. Get here. Ability, cooldown, meat, food progress. Yeah, please. Come here, you. Ouch. Leech, immune system, revenge. This looks good. Banana, I want that. Oh boy, boss is coming. Oh, that's a lot of food. That's a lot of food. Scales, ability, cortex, body slim. Oh man. I'm already in the ability build, so I'm just gonna... Oh, okay. Ouch. Come on, man. Oh. Ouch. Ah. Come on, hit me. You hit like a girl. Ouch. Quoting. Yes. I quote you. Revenge. Stinger. Revenge. Yay. Wings. Yes, please. Bat wings. Stupid cat. Ouch. Oh wow, that's a pack. Holy crap. Alpha, come here. Ouch, that hurts a lot. Attack area courting. Leech. I don't know which one. Harms the nearest enemy at target direction. On death cooldown. Attack area. What the? Ouch. Brother, come on. That hurts. Jesus. More mash. I'm pressing Q. Why aren't it working? Oh, it's cooldown. Damn it. Ouch. Oh, that hurts. Oof. Oh my god. Replay. Cheek pouch. Oh, yes. I want to check something. Pause fire. Really? CPH. Really? Interesting. Nobody plays Crossfire here? Jaws. Ooh, cheek pouch again. Nah, Jaws. Ooh, trunk. I guess so. We'll take it for now. Look at him. So cute. Perfect. Dodge. Yeah, I like that. Free food. Hell yeah. Oh my god, so much free food. Scavenger. Right on time. Jaws. Spine. Social-based evolution. Yeah, let's go with social build this time. I wanted that alpha, but he's already gone. Ouch. Oh, I don't think we should challenge him right now. Oh god. Cancel. Movement speed has diminishing returns. Enemies HP increased. Hollow bones. Tail. Yeah, let's go with tail. Go social. Cutaneous fat. Yes. I hate the fact that I lost cheat pouch. Oh, bounty! Oh my god. Bait. Food. Oh boy. Ouch. Stop it. Scavenger. Social. Ouch. Oh man, this is way above my weight class. Oof. Come here, you. Gotcha. Oh. Yes, that's it. Come on, one more. Okay. I really need an attack right now. Ouch. Owie, 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 owie. Stop it. Okay. Back area, scavenger, subcutaneous fat. Fine. Reach. I need more reach. Food. Food. Ouch. Oh, come on, leave me alone, leave me alone. Stomach's alive. Oh. Man, why are you giving me... I'm getting a choice between two good things that I want. Saliva and jaws. I want attack, but I also want feeding speed. Should I pick the shiny one? Nah, jaws. Ow. Stop bothering me. Generative tissue, more eyes, antlers, more eyes. Shoot. Atlas saliva. Scavenger. Food always tastes better when it's free. Ooh, points of interest. Oh, they're in water though, and I'm about to fight the boss soon. I'm gonna stay here for a bit. Jaws. Nice. I think I might take a neck bite. No, I'm just gonna take that. Whoa. Ouch. Ow. Oh, missed. Come on. Should have got more. I mean, I never really got the option to do more physical damage. Yikes. Nice. Get wrecked, buddy. Get wrecked. Tentacles. Speed. Wings. Whee! Now we can go to the point of interest. Hell yeah. Ooh, max HP. Right. Jaws is physical. HP. If we get body slammed, that would be really good. Oh, but we eat so slowly. Run away! Stop chasing me, bro. Meaningful, yes, please. Oh, small. Small. One more, please. Ouch. Don't run away. Speed. 7. Ooh. Immune system, please. Boy, am I glad I took immune system. Ooh, free food. Oh, more free food. Stomach. Get wrecked, buddy. Oh my god, so much meat! Attack area, tail wag. Yes, finally. Ouch. Small. Oh, charmed. Nice. It's too cold out. Okay. Yeah. Free food. Whining. Ouch. Ooh, alpha. So many alpha. Oh my god, that's... I hate them. I hate alphas. Alright. I think I'm gonna call it a day. Bye. See ya.